This is an interview with David Hann, a statistician whose work sits at the intersection of data science, real-world decision-making, and how we misread what data is telling us. He's the author of Principles of Data Mining, the Improbability Principle, and Dark Data. And he's worked across academia, government, and industry, including 8 years as chief scientific advisor to a leading hedge fund and 8 years on the board of the UK Statistics Authority, which oversees the Office for National Statistics. You can read more about David Hann on our website, 6degrees.blog, and our Instagram page, 6 Degrees Away. Thank you and enjoy this video.
What first drew you into statistics and set the direction for your career?
Okay, so I really fell into it by accident. When I was very young, when I was a kid, I was no good at maths. I was bad at maths. And we're going back a long way here. Computers then arrived. Concepts like binary arithmetic, which of course everybody's totally familiar with now, but you know, nobody had heard of it in those days. No kid at school had heard of it in those days. And I got fascinated by computers. I used to read a lot of science fiction, and you know, suddenly there were these giant electronic brains people were talking about. The sort of science fiction had become real kind of thing. That led to me getting interested in maths, working hard and getting better at it. And so I took a degree in maths. That was all very well, but then when I graduated, I had to decide what I wanted to do. The trouble was, I was interested in lots of things, you know, and I couldn't make a decision because doing one thing necessarily means not doing another thing. My tutor suggested my tutor at university suggested I should think about becoming a statistician, doing statistics, because he said there were always jobs for statisticians. So that's what I did. I did a master's degree and then a PhD in statistics. And stop me if you don't want me to go on at such length, but I should say at this point that maths and stats are really opposites of each other. Over here we say maths, but you know, math and stats are really the opposite of each other. Mathematics basically says, given these axioms and rules, how you combine things and so on, what would the world, that is what data, what would it look like? Statistics does the opposite. It says, given these data, what world could have generated these data? So really they're going in opposite directions. But anyway, for me, the accident of discovering statistics was a godsend, because you can work anywhere with statistics. There's the American statistician, John Tukey, is very famous for a number of reasons, but one reason he said, statisticians play in everyone's backyard. And it's absolutely true, although I've been based in the academic sector for most of my life, working at universities, I've worked very extensively with government and industry. For example, I served on the advisory boards of a couple of the major pharmaceutical companies. I worked with most of the major consumer banks and credit scoring agencies. I spent 8 years as chief scientific advisor to one of the world's leading hedge funds. I served for 8 years on the board of the UK Stats Authority, which oversees our Office for National Statistics, like your Statistical Bureau and so on. So I guess you could say that I still haven't decided what I want to do when I grow up, but statistics means that I don't have to, because I can work anywhere. And I would like to say for anybody who happens to be listening to or watching or whatever this, that statistics is a really great discipline for a career. You can tackle fascinating problems, you can solve important problems which benefit humanity, and you can find jobs which get paid very well. I can't guarantee that you can find a job which will do all three of those things together, but through statistics you can do those things.
From your early work on classification to today's deep learning, which principles should still guide how we build classifiers?
Yeah, so a lot of my work has been concerned with building what are called supervised classification algorithms, where you have a data set, and using that data set, you build a rule, an algorithm, a model, which will allow you to assign new objects to classes, like has this person got disease A or disease B? Is this spoken word yes or no, and so on. That's what a classifier is. It's difficult to answer this question because it's so context dependent. It depends so much on the problem. But maybe that's the answer with a couple of parts. I think first you should always take a step back, pause, think about what you really want to do. For example, you might think, how representative is my sample of data that I've got to build a model of the population I'm interested in? You might want to think about, do you want to minimize the proportion of sick people you classify as healthy or healthy people you classify as sick? Or what are you trying to do? Combination of those two things, or what? And then, so that's what you do at the beginning. Take a step back, pause, think exactly what you want to do. That's one aspect of the principle. The other one would be sense check your answer at the other end when you've done your analysis and you've got an answer, sense check it. Think about whether that answer really makes sense. For example, in many medical screening problems, medical screening sounds like a good idea. Identify those people who've simply got the disease so you can treat them. But in many medical screening problems, they cause more damage than benefit because of all the interventions made on healthy people that it's misclassified as sick. So really, sense check, think about the answer. So I guess you asked what the principle was, and I guess the answer was, in a nutshell, be cautious, be careful. Don't be seduced by the power of the tools we've now got available, like deep learning and so on. And don't rush in without connecting your brain. I guess that would be the principle.
Do you have any rules of thumb to decide when a tiny accuracy gain is not worth the extra complexity of finding maybe this much more data or this information?
I don't have any rules of thumb because, again, it's very context dependent. It will depend very much on the problem. But that's a really good question. And that is certainly something people should always consider. And, there are plenty of examples where people have got a perfectly adequate answer and then spend a lot of money unnecessarily pushing it, refining it, and so on. So that's a very good point. But I think the answer is context dependent. It depends exactly what you're trying to do and what the problem is.
Which single idea from principles of data mining do you think practitioners undervalue today?
Yeah. So Principles of Data Mining is one of my books. Which single idea do people undervalue? Well, again, I think that's a very tough question. Context dependent, perhaps. I guess it might be, okay, here's the thing. I guess it might be that understanding is the key. The tremendous interest we've seen in the last few years in data science and AI has all been driven by what I call data-driven models. These are analyses which basically look at the data, identify relationships, features, correlations, whatever in the data. They're not driven by some underlying theory like Newton's laws of motion or anything like that. They're all data-driven. And I think it's all very well building a data-driven model, like a deep learning neural network, which capitalizes on these observed relationships. But if you don't think about what those relationships mean, there's, I think, a significant risk that things can go wrong, they can go awry. And I think hallucinations in large language models are a great illustration of that. How these chatbots, Chat GPT and all these others can sometimes come up with nonsense. And I think they're an example. They've seen a relationship in the data, so they say this is the way it is, but they're not relating that pattern in the data to anything in the real world. They don't have any idea of the semantics, the meaning, the real world meaning of the things. So I think that is probably the single thing that people undervalue. It's understanding what's going on rather than just looking at patterns of relationships. But that's a sort of top of my head sort of answer to your question, and a very quick one, a very superficial one. Maybe if one thought about it more deeply, one would come up with some other answer.
So you think people jump to conclusions too fast when looking at data?
I think they're perhaps, in many situations, too ready to accept what comes out of the computer as the answer without thinking carefully enough, does this make sense in this context? Probably only a tiny percentage of times does this happen, but it does happen, yeah.
In a high-dimensional system, where do anomaly detectors go wrong?
So anomaly detectors are systems which look at your data and say, this data point, this little configuration of data points, this group of data points, whatever, are anomalous. They're unusual. They stand out from the others. So that might mean that they're valuable. That might mean that they're interesting. You might have made a major scientific discovery. And in one of my books, I give examples of this where people spotted anomalies and got Nobel Prizes as a result. But of course, anomaly detectors can go wrong as well. And I think you put your finger on something there. In high dimensional spaces, if you've got enough dimensions, in any finite data set, every data point can be regarded as anomalous, because in some way, if you've got enough dimensions, every data point is different from the others. So with high dimensions, you have to be particularly careful. And perhaps people haven't always taken that into account. So perhaps the answer to your question, where do they most go wrong, is by failing to give an explanation or rationale, understanding again, we're back to understanding, for describing a point as anomalous. So perhaps they don't exactly go wrong, but they might not be very useful. I guess another possible reason might be that the underlying populations are changing over time. The point identified as anomalous could simply be an early point from the fact that things are changing, that the population's drifting. And the fact is that the world we live in is fundamentally non-stationary. It changes over time. Look at the economic situation, look at the political situation. The world changes. And so a point which looks anomalous might just be the fact that it's reflecting how things have changed.
Again, you believe that we shouldn't jump to conclusions with these detectors as well.
You've put your finger on it. Exactly. Connect the brain. Yeah. Don't jump to conclusions. Think, is this meaningful? Is this sensible? And that will stop us making so many mistakes. Yeah, exactly.
In credit scoring, how to boost fairness and interpretability without losing performance?
Yeah. This concept of fairness is a contested one, I have to say first. The answer to your question is decide exactly what you mean by fair first. That's the most important thing. Contested here means that there are many definitions of fair. And in fact, it's mathematically provable that some of the definitions are mathematically contradictory. If you accept this as your meaning of fair, then this one necessarily is unfair. I'll give you a very simple example. By fair, we might want to mean that equal proportions in two categories are granted credit. Let's be blunt here. Equal proportions of men and women are granted credit. Surely that's fair. You're giving exactly the same proportions. But we might alternatively want to mean by fair that lower risk categories get more credit. They're more readily granted credit. Now, these two things, if one category has a higher risk of default than the other, you can't satisfy both of these criteria. They're contradictory. And as a sort of corollary of that, or comment on it, I should say that men are more risky than women, younger people are more risky than older people. So, this is a real sort of issue. So step one would be first to say, what definition of fairness are you talking about? And only then can one try to, improve accuracy, improve performance. Probably doesn't really answer your question, but well, anyway.
So I guess the challenge is finding what society sees as fair.
Yeah, well, society in general uses a lot of different definitions. I think the real challenge is for your context, for your problem, for the situation that you're working in, to decide, agree what definition of fairness you want. But basically what you said, yes.
For the improbability principle, what misconception about randomness did you most want to correct?
Okay, so the improbability principle is another one of my books. And I guess here it was the notion that when we experience some wonderful coincidence, I wanted to sort of correct the notion that it must have some mystical or supernatural explanation or meaning. The truth is that when we experience these amazing coincidences, these sorts of events, you can explain them by the mathematics of probability. Having said that, and that's what my book does basically, but, and this is an important sort of corollary, an important additional comment, I would like to add that the fact that you can explain these highly unlikely events, people winning lotteries or whatever, should not detract in any way from the wonder and delight we experience when we feel when we experience such an event. So, for example, a couple of years ago, I signed up with a new optician, and I found there was another David Hand there. It made me smile. I can go back and do the calculations, how many David Hands there are in the UK, this sort of thing, calculate the probability of it, and think, oh, well, it's not at all surprising that during my life I shall encounter another couple of David Hands. But it still made me smile. And, just because there's sound maths behind it shouldn't stop you enjoying this sort of
thing. Do you think the public tends to overestimate intent behind consequences and coincidences? Sorry.
Yeah, I think it does. Perfectly reasonably. I mean, I can say, and as I discussed in my book, there's sound maths behind it, but you can't expect everybody to have spent years studying the mathematics of probability. And when they experience these things, they think, wow, what's the chances of that? Clearly, for them as individuals, it's a very small chance. But of course, they're not putting it in the context of 8 billion people in the world. So there's a lot of opportunities for these things to happen. And so when they experience it, they think, what are the chances of that? There must be some reason for it. There must be some explanation. You have to bear in mind that sort of the human brain has evolved to take note of events in the world. So when you see the grass moving, you think, my God, it might be a lion. You connect, it might be about to eat me. You connect these things up. So when something unusual happens, a coincidence, this other David Hand popping up, you think there must be some reason for it. It's the way the human brain has evolved.
In real projects, what kind of dark data most often flips a conclusion once it is uncovered?
Yeah, I think again, this question is probably so context and problem dependent it's impossible to answer in general. But I think maybe a sort of high level answer is that non-representative data is the most problematic issue, and I do see this a lot with problems I'm asked to look at. If your data are distorted in some way from the population you think you're describing, then your conclusions can be completely misleading. Again, we're back again to the earlier point. It means that you need to think very carefully indeed about how the data have been collected. What's happened to them before they reached you? Have they been cleaned or transformed in some way? After all, the fact is that data that is clean for one purpose may not be clean for another, might be very different for another. The cleaning purpose for one problem, one objective, might mess things up for another. So here's a totally trivial and indeed obvious example. Suppose I wanted to study the movements of people around London. One way I could do that, I could get data from the subway operators, the train operators, about tickets and electronic passes movements. And I could analyze that data and say, this is what happens. That's all very well. But of course, I'm missing all those other people who travel by car or walk or cycle or whatever. And I could get a very misleading impression of what's going on. In fact, my book, Dark Data, has got a lot of real life examples of how people have been misled by that sort of misrepresentation, selection bias of the data that you're working with, and how it's led to fatalities and lost fortunes and those sorts of things.
So if someone is limited in resources, how should they, can they, and if so, how should they look at data to best identify these this dark data?
Yeah, yeah, absolutely. Again, I think we're back to the earlier point, be cautious. Think very carefully about how the data might be misleading. What might have you missed? And in my simple example of movements around London, it wouldn't take much thought to think, trains, subways, but what about all the other, that in that example, you could very readily identify it. Perhaps also another answer is get other eyes to look at the problem. More eyes, fewer lies is, an old saying. Get other people's perspective. They might be able to think of things you haven't thought of. So those would be things. Of course, I have to comment that you can never guarantee that your data aren't distorted, but you can do the best you can. But there aren't any guarantees in real life. You just do the best you can.
What technique has proven most effective for explaining statistical uncertainty to a broad public audience?
Yeah. And this is probably really this is really a tough question, which probably merits a long answer with a lot of different techniques. But I guess the best approach is to give and explain the meaning of a range of values. So rather than saying my best estimate is this, I predict this, because once you've given an actual single numerical value, people lock onto that. So rather than do that, I would say something like, we obviously can't tell for sure, but we think it's most likely to lie between X and Y, 3.5 and 4.2 or whatever. So that you're giving people a range right from the start. But you've, again, put your finger on something absolutely vital there. In general, people find it difficult to cope with uncertainty, are uneasy about, perfectly naturally, are uneasy about uncertainty, much prefer concrete answers. Have I got this illness? What am I suffering from, doctor? You don't really want the doctor to say, well, it might be this, might be that. Don't really know. So it's difficult. People don't like uncertainty, but I think the answer to your question, give a range of values.
So if for any reason the data widens or the data seems to point a different way, how do you maintain your trust with the public?
Yeah, that's a very good question. And of course, you see that so often with official statistics. The estimate of GDP is this. And then next month you say, no, we got it wrong. It should have been that. GDP, gross domestic product of an economy, is a good example because the way that's estimated is you get a rough initial estimate on some of the data coming in, and then more data comes in, so you revise it, and then more. So you get different revisions of how the economy is doing, even at a particular time as more data comes in. And again, I think you really put your finger on a key issue here. I think the only thing you can do is try to explain to the public that there's uncertainty about this. So perhaps in your initial estimate of GDP, when you say, based on the limited data we've got so far, this is what I think it is, rather than saying, this is what I think it is, you should say, we think it lies high probability, and you can stick a number on that probability if you like, of lying between these two values. So again, range, I think.
Looking back across your research and books, which contribution do you most hope endures?
Yeah. It is a tough one because things change. And what was important when it was discovered or created becomes less important as time passes. Brilliant things I did when I was young, or at least I thought so at the time, I probably don't think are so brilliant now. It's in the nature of things, and I think especially in science, of course, where progress in science necessarily means the old ideas of the past, they no longer hold. Interestingly, it's less so in the art, where a beautiful picture or novel or play or whatever can stay beautiful or remarkable over time. Like, think of Rembrandt or Charles Dickens or Shakespeare. Hundreds of years onwards, we still say this is good, whereas science tends to be surpassed. Oh, there's another point here. It's also true that it's in the nature of things that I always believe the work I'm doing at the moment is the most important, and I hope will endure whenever that moment is. So the answer is it's what I'm working on at the moment.
Do you was there a view you had before or a study you published that today you wouldn't agree with or you would revise?
Revise, certainly. A lot of my stuff, you know, I've understood more, I've done more work. Um, Other people will have worked in the same area and pushed it forward, shown I was wrong, or shown how to elaborate or extend it or whatever. Again, that's in the nature of scientific work, that it gets pushed on and extended. Um, I can't I can't put my finger on anything, an example at the moment that I think was overtly wrong. I can I could think of things which sort of where my understanding has improved, but
And is there an issue or a concept that you would be interested in the new generation taking on?
um, there are all sorts of things. There are all sorts of areas which need deeper investigation, and one of them relates back to what we were saying earlier. This is how to gain understanding from, and it relates to a particular sub-question you raised, how to gain understanding from inadequate data, from distorted data, from selected data, and how to allow for the selection and so on in more detail. More work is needed in this area. And it's becoming increasingly important. Governments used to take surveys to rely on to understand how the population felt about things and what they should do and so on. But over the world, over the last 10 or 20 years, response rates to surveys have been declining. So previously, you might have got 90% of the people you asked gave you an answer. And the people you asked would be very carefully, randomly selected, so you got good coverage of the population. But now, the response rate might have fallen to as low as 30% or less. 30% of the people you wanted to answer are answering, which means the bulk of the people aren't telling you. And you don't know if that 70% missing are different from the 30% you've got. So increasingly, people are turning away from surveys to what's called administrative data, which is things like tax records, medical records, education records, all the records that are kept when you make some transaction or do anything. And this also applies to things like you buy something on Google or you go on Facebook or whatever. But these are not random samples. They're not representative of the population. That could be distorted in unknown ways. So I think that a lot, and people are working on this, of course, and people are finding answers, but I think that's something which a lot more work needs to be done in the future.
As founding editor of Statistics and Computing, how do you describe the relationship between statistics and data science today?
Yes, okay, that's a good question. Statistics and Computing was a journal I launched in 1991, so a long time ago now. Because I realized then that the two things were sort of beginning to merge. And in some research areas, they overlap. Anyway, basically, I describe data science as mainly statistics, but combined with computer science, and also combined with understanding the domain it's being applied to. So if you're working in medicine or finance or whatever, they have special, all the data and the problems in different areas are subtly different, have different questions, different types, different properties. So you need to understand that. But data science, I would say, is mainly statistics. Statistics is, after all, the science of extracting understanding and illumination from data. And of course, that's primarily what a data scientist tries to do. So data science is basically fundamentally statistics, but with an important input from these other things. And I think without a good understanding of statistics, not possible to be a good data scientist.
Is there any what do you suggest that data scientists learn from statistics and vice versa?
Okay, I think they will learn things like how to make inferences, how to draw a conclusion about a population from merely a sample. They will learn how to best display data, so that you can clearly see what the relationships are and what's going on in the data. Indeed, how to display the data so that you can discern things that you couldn't discern if you displayed them in other ways. So there are fundamental things like that.
For government use of predictive models, what safeguards should be non-negotiable to protect transparency and trust?
Excuse me. Yeah, this is a topic as well. I think it's difficult to pull out a single thing. Excuse me. Too much talking. This is nature's way to tell me to shut up. It's difficult to pull out a single thing, but I think interpretability is very important. So when a model makes a prediction, the reasoning behind that prediction can be presented. And perhaps that should be coupled with a right to receive an explanation when one is requested. Oh, my goodness. Up you.
What single piece of advice would you give a young statistician about balancing mathematical optimality with interpretability?
Yeah, I think that is a very nice question to conclude with, in fact, because I think the short answer is that in most real life problems, a good solution is more valuable than the best solution if that good solution comes with other attractive characteristics, such as being much simpler to implement, being found more quickly, being comprehensible, which really means interpretable, and so on. Let me give an example, although it's not really a question of interpretability. An example I sometimes use when discussing credit card fraud detection systems, is that a perfect system which correctly identifies all fraudulent transactions and all legitimate transactions would be useless if it took 3 months to classify each transaction. Much better a system which only got 90% right of each right, the legitimate and the fraudulent ones, if it did it while the transactions were being made. So good. Actually, there's an old saying, isn't there? Best is the enemy of good. Oh my God.
Sorry.
I don't give so many talks nowadays, so going on is a bit tougher for me.
And I have one last question, which we ask
Okay.
all of our interviewees, and it is, how do you define success both personally and professionally?
How do I
Define success both personally and professionally.
I'm not sure I've ever been asked that before. That's a very good question. I suppose that people are interested in what you do. That would be both personal and professional. That what you do, I guess my answer has got lots of parts. One, that people are interested in what you do has a beneficial impact. And you find it interesting. Oh, this is important, isn't it? Because that has implications for the jobs people do. Get a job that you enjoy. Don't just do it for the money, because you never know when things might end. But you certainly don't want to be in a situation, where you've just slogged away and never get to enjoy it. So find a job that you enjoy. And I think I've been very lucky with academia. I've been able to come back to the things we asked right at the beginning. Why did I become a statistician? Because I didn't know what I wanted to do, and I could go in whatever direction interested me. And I think that would probably be, in that way, I've been successful. We won't go into all the many ways that I think I've been unsuccessful, because that would take us too long.